In this lesson, we will look at thermal ice protection systems, as used on many turbojet aeroplanes, including the Boeing 737. A thermal ice protection system is one where the surfaces to be protected are heated. One major advantage of this system over mechanical systems is that there is no change in the profile of the surface being protected. This heat may be provided by hot air, electricity, or hot oil, although this method is rarely used. The most common method of thermal ice protection is the hot air system. There are several methods by which the heated air can be supplied, and these include the bleeding of air from a turbine engine compressor, the heating of ram air by passing it through a heat exchanger located in an engine exhaust gas system, and the heating of ram air by a combustion heater. The areas normally protected by a thermal system include the engine air intakes and compressor inlet guide vanes, plus the wing leading edges and slats if they are fitted. On some, but not all aircraft types, the tailplane and fin leading edges are also protected. In systems supplied with compressor bleed air, the hot air is tapped directly from the engine compressors. The air is normally taken from a low compressor stage and a high stage to ensure the temperature and pressure is sufficient at all engine speeds. The amount of air tapped off is a very small proportion of the total airflow through the compressor, so the effect on engine thrust output of using compressor air for ice protection is similarly very small. The bleed air temperature may be controlled by a pre-cooler using fan air before it passes into a bleed air manifold. From here, the air supply to the areas requiring ice protection is controlled by shut-off valves. In some systems, these valves are able to modulate to maintain the air pressure within acceptable limits. The exhaust gas heat exchanger method of supplying warm air is employed in some types of aircraft powered by turbo-propeller engines. The heat exchanger unit is positioned so that exhaust gases can be diverted to pass between tubes through which outside air enters the main supply ducts. The outlet temperature is usually regulated by a device, such as a thermostatically controlled flap, fitted in the ducting between the exhaust unit and the heat exchanger. In a combustion heating system, ram air is passed through a cylindrical jacket, enclosing a sealed chamber in which a fuel-air mixture is burned. The ram air is heated by contact with the chamber walls. Air for combustion is derived from a separate air intake and is supplied to the chamber by means of a blower. The combustion heater is fully explained in the pneumatic systems lesson. The hot air systems used for airframe ice protection on modern turbojet aircraft generally use engine bleed air and are normally anti-icing systems. In systems of this type, hot air is supplied to a pipe or duct running along the inside of the leading edge sections to be protected. These ducts are known as spray or piccolo tubes. The duct has spray holes in it, through which air is allowed to escape and heat the leading edge, melting any ice that has formed and preventing further ice formation. The air is then ducted rearwards before being dumped overboard through holes in the lower surface. The system is controlled by flight deck switches, which operate valves in the pneumatic manifold to shut off the airflow when ice protection is not required. Engine air intake de-icing or anti-icing can be achieved either using hot bleed air or an electrical resistance heating system. Electric heating is usually only found on propeller-driven aircraft, where the propeller is also de-iced by electric heat. On other types, electricity is usually only used to heat smaller components, such as windscreens and pitot heads, because of the high currents required. A typical hot air engine ice protection system is shown here. The air is tapped from the compressor at a suitable point. It passes through an electrically operated control valve, which is actuated by a switch on the flight deck. The air heats the inlet guide vanes, the nose cone, and the air intake cowl. The air is then exhausted either to atmosphere or back into the air intake. In an electrical heating system, heating elements, either of resistance wire or sprayed metal, are bonded to the air intake structure. The electrical power supply required for heating is normally a three-phase alternating current. In the electrical wire type of system, the elements are sandwiched between layers of glass cloth, impregnated with resin. In some systems, the elements may be sandwiched between layers of rubber. The outer surfaces are, in all cases, suitably protected against erosion by rain and the effect of oils and gases. In the sprayed metal system, a base insulator is brushed directly onto the surface to be protected, and then the electrically conductive metal is sprayed onto it. A further insulating layer is applied on top of this. The outer surface is then given a suitable protective coating. The resulting protected surface is known as a spray mat. In an electrically heated ice protection system, both anti-icing and de-icing techniques are employed by using both continuously heated and intermittently heated elements. The system is controlled by switches on the flight deck. When the control switch is placed to on, the power supply is fed directly to the continuously heated elements and via a cyclic time switch unit to the intermittently heated elements. The cyclic time switch unit controls the application of current in selected time sequences, compatible with prevailing outside air temperature conditions and the severity of the icing. In this example, the output of the time switch can be changed by selecting either light or severe icing conditions. The cyclic circuit is arranged so that while the supply is on for some heaters, it is off to others, and vice versa, in order to maintain a constant de-icing load to the electrical system. A number of small components are electrically heated to prevent ice formation. These and the windscreens are the only items normally electrically heated on large turbojet type aircraft. Some of them, such as pitot heads, angle of attack sensors, and temperature probes, may have switches and warning lights in the cockpit. Others, such as wastewater drain mast heaters and the inline heaters fitted to water pipes, operate whenever the aircraft's electrical system is powered. That is the end of the lesson on thermal ice protection. You now know that the heat source for thermal systems can be hot air, electrical power, or, very occasionally, hot engine oil. You should understand that airframe ice protection on modern turbojet aircraft is normally achieved using hot air bled from the engine compressors, with very little loss of engine thrust. These systems are usually anti-icing systems. You also now know that the engine intake can be heated using either hot air or electrical power. If hot air is used, the system will be an anti-icing system. But if electrical power is used, there will usually be a combination of de-icing and anti-icing. Finally, you should know that on turbojet aircraft, electrical power is normally only used to heat the windscreens and smaller surfaces and components.